Today we'll take the derivative of a composite function. The derivative with respect to x of f of g of x. This is known as the chain rule in calculus. The derivative of f of g of x is the derivative of f of g of x with respect to g of x times the derivative of g of x with respect to x. So we take the outer form and treat what's there as variable, and then we take the inner form and take the derivative with respect to x. Let's look at an example. This is the best way to understand. We'll take the derivative with respect to x of sine the quantity x squared plus 1. Here we consider f of g of x to be sine x squared plus 1 and g of x to be x squared plus 1. So we're treating x squared plus 1 as a variable, and then we're going to take its derivative. Since the derivative of the sine is the cosine, the derivative of sine x squared plus 1 with respect to x squared plus 1 is simply the cosine of x squared plus 1. But we're not finished. We didn't take the derivative of the sine of x. We took the derivative of sine of x squared plus 1. Then we have to take that into account. So then we must take the derivative of g of x with respect to x, which is the derivative of x squared plus 1 dx, which is 2x from the x squared using the rule of derivative of x to the n equals n x to the n minus 1. And the derivative of the constant is 0. So the derivative of sine of x squared plus 1 with respect to x is 2x cosine x squared plus 1. What is important is that we take the derivative of the outer form first and work inward. If there's a third part, such as f of g of h of x, we need to work all three parts. And that's why we call it the chain rule. We'll have to take as many derivatives as needed. But it's not any more difficult in normal functions where we have only two parts than taking two derivatives. So let's not make a big issue of this. We'll practice a little. Find the derivative with respect to x of the cube root of x squared plus 4. It's best when you have cube roots to write it in friendly exponent notation. So we have the derivative of x squared plus 4 to the 1/3 dx. And we'll treat x squared plus 4 as first variable and take the derivative. We get 1/3 x squared plus 4 to the negative 1/3. Then we look at taking x as the variable of the inner part, which is 2x, the derivative of x squared plus 4, 2x. And so we can write this as 2x over 3 times x squared plus 4 to the 2/3 power. Another example from functions that you should be familiar with by the time you get to the chain rule, we're going to take the derivative of e to the x cubed. Now, the first thing is we're going to take the derivative e to the x cubed with respect to x cubed, and the derivative of e to something is e to the something, so we get e to the x cubed. Then we have to take the derivative of the inner part, the x cubed, which is 3x squared. And so our derivative of e to the x cubed with respect to x is e to the x cubed times 3x squared. Or you can write the 3x squared times e to the x cubed. It doesn't matter. The chain rule can occur within the product rule or the quotient rule. Also, the chain rule can contain the product rule or the quotient rule. Uh, it's going to happen wherever it will, and when we get to the point where we have to take the derivative of a composite function, we simply follow the rules.